if we know the acceleration equation for an object, and if we are given initial conditions for the object's velocity and position, integration allows us to find the velocity and position equations for the object. So remember that for differentiation, the derivative of the position function is the velocity function, and the derivative of the velocity function is the acceleration function. For integration, we go the opposite way. The integral of the acceleration function will give me the velocity function, and the integral of the velocity function will give me the position function. The acceleration of a particle at time t is given by a of t equals 4t minus 3. The velocity at time equals 1 is 6, and the position at 2 is 5. Find the velocity equation. Let's remember that the velocity equation is the integral of the acceleration equation, and we will be integrating with respect to the variable t. The acceleration function, 4t minus 3, will be our integrand. Remember that if you're taking the integral of a sum or a difference, you can separate the integrand into two separate integrals, taking the integral of the first part minus the integral of this second part. This only works when you are adding and subtracting. Now the scalar multiple rule states that if I'm multiplying 4 times t inside of the integral, that I can actually factor out any number. Anytime I can factor out a number out of an integral, but never a variable. I will factor out this 4, so it'll be 4 times the integral of t with respect to t minus, and here the 3 is the only thing that's there, so factoring it out doesn't really help me integrate any more easily. Now we will integrate. 4 will be multiplied by the integral of t. Our reverse power rule would be t is now to the power of 1, so we're going to add 1 to that power, so t will be to the power of 2, and we're also going to divide this by 2. X to the n plus 1 divided by n plus 1 minus the integral of 3 is 3t plus c. After reducing, I get 2t squared minus 3t plus c, and this is the velocity function, except it has a plus c in it. I think we were given information earlier that could help us actually find the velocity function. So if v of 1 is 6, that gives me enough information to be able to solve for c. That means that when I plugged in 1 into the velocity function, I should be getting out 6. So the output would be 6 when I plug in 1. Use this to solve for c. I ended up getting c is equal to 7. So my velocity function is 2t squared minus 3t, and it's not plus c because I have a value for c now. It is plus 7. Find the position equation, S of t. The position equation is the integral of the velocity equation. So we need to integrate 2t squared minus 3t plus 7 with respect to the variable t. In order to integrate this polynomial, I'm going to separate it by individually integrating each term. The integral of 2t squared dt minus the integral of 3t dt plus the integral of 7 dt. Scalar multiple. Anytime you have a number being multiplied by these variables, you can factor that out of the integral to make your life just slightly easier. So this is 2 times the integral of t squared dt minus 3 times the integral of t dt plus Again, taking 7 out doesn't really make our lives easier. The integral of t squared is t to the 2 plus 1, and that 2 plus 1, or that 3, is also the denominator, minus 3 times, this is t to the 1, so it should be t squared over 2, plus 7t plus c. This is the position function. Let's reduce that, though. And the additional piece of information they gave us was that s of 2 is equal to 5. So my output should be 5 when my input is 2. And this will give us an equation that we can solve for c. Once you solve that equation, you should get c is equal to negative 25 over 3, which makes our final position function what we had here, but now substituting our value for c. Given that on Earth the acceleration of an object due to gravity is negative 32 feet per second squared, negative indicating downward movement because gravity pulls objects down. So we're going to, from that, develop the equation for the velocity of the object. And they've given us some notation that may help us. That initial velocity is written as v sub 0. Velocity is the integral of the acceleration function. So the acceleration here is negative 32 feet per second squared, negative 32 dt. The integral of a number is just that number as a coefficient of the variable plus c. This is our velocity function. As you can see, velocity function here is a line, and so c would technically represent our y-intercept, right? The y-intercept of a line gives you somewhat of a starting point, an initial value that the slope can help to build off of. In this case, our initial value, because this is a velocity function, is simply the initial velocity. Who knows what that is? In this case, this is just a general form, so we don't know what the initial velocity is. But c, the constant of the integral, in this case can be more accurately represented by v sub 0, the initial velocity, because this is the velocity equation. The equation for the position of the object, and they've also given us s sub 0 is our initial position. The position equation is the integral of the velocity equation, and our velocity equation was negative 32t plus the initial velocity, integrating with respect to time. As before, I could separate this to be negative 32t, the integral of negative 32t, plus the integral of our initial velocity, of course all with respect to time, and scalar multiple, I will take that out. Negative 32 will be multiplied by the integral of t, that is t squared over 2, plus the integral of the initial velocity. Initial velocity is just going to be a number, so you're integrating a constant here. When you integrate a constant, the constant becomes a coefficient of a variable to the power of 1 plus c. The position equation, when we reduce here, is negative 16 t squared plus the initial velocity times time plus c. And in this case, we could more specifically label c because this is giving us the position, and the position at time 0 is your initial position. So if I were to plug into 0 into these values of t, I would be left with the constant, or the initial position. Now, these equations that we just found actually work for many problems. Anytime that you have an object falling on Earth, and when those units are feet per second, then you can use this as your velocity equation and this as your position equation. And you would just plug in the initial velocity given to you in the problem and the initial position given to you in the problem.